Ladies and gentlemen, now, we will start the first lecture of the last phase of Lean Six Sigma project, the control phase. Where are we? During the improved phase, the solution is piloted, and plans are made for full-scale implementation. Putting a solution in place can fix a problem for the moment, but the activities in the control phase are designed to ensure that the problem does not reoccur, and that the new processes can be further improved over time. In the control phase, we will control the process, implement control charts for key variables, mistake-proof processes, and evaluate results. The module will be divided into 3 lectures. It includes the following documents for download: the course material in PDF, templates for control chart, instructional videos for control chart tools using Excel, Sigma Excel, and Minitab. During the module, the following topics will be covered: visual process monitoring, basics of control charts, control charts for continuous data, control chart using Sigma Excel, control chart using Minitab, control charts for discrete data, standardization, reaction plan, process management diagram. Goals from visual process monitoring are: inform about the day-to-day performance at a glance, enable direct feedback to the employees, prioritize tasks, transparency over the workflow, recognize deviations from standards in an easy way, ensure that safety, health, environmental, and cleanliness concerns are being met. The steps are: 1. Production survey boards and boards. Production survey boards monitor the results of a process and allow us to judge if they are meeting customer needs. 2. Production process boards. These boards focus on providing information on improvement projects or current process management. 3. Personal performance and training boards. This board provides a list of all employees and helps to determine the employee's training need. 4. 5S or Kaizen boards. They indicate the status of 5S or Kaizen actions. An example for the visual process monitoring. Control charts are similar to run charts. They display measurement data in time order. However, they are used to distinguish between process variation resulting from common causes and variation resulting from special causes. The average, mean, is used for the center line instead of the median used on the run chart. While interpreting control charts, we also talk of 2 indicators. Leading indicator. Leading indicator shows the trend before the defect occurs. For example, you may be able to see a trend of 6 downward points. This is leading indicator that the process will produce a defect outside the lower control limit. Lagging indicator. A lagging indicator is an outlier that is already outside the upper or lower control limit. This is a lagging indicator that the defect has already occurred in the process. Defects and defectives. A defect is any item or service that exhibits a departure from specifications. A defect does not necessarily mean that the product or service cannot be used. A defect indicates only that the product's result is not entirely as intended. A defective is an item or service that is considered completely unacceptable for use. Each item or service experience is either considered defective or not. There are only 2 choices. The goals are process monitoring, recognize and pursue process spreads over time. Find out if the process is stable and under control. Identify common and special causes. Set out the tools for steering the process. Confirming the impact of process improvement activities. Data requirements, minimum of 25 consecutive subgroups, or minimum of 100 consecutive observations. Must be in time series order. Control limits are not specification limits. Control limits are based on data and tell you how a process is actually performing. Specification limits are based on customer requirements and tell you how you want a process to perform. Control limits and specification limits are not interchangeable, and they are completely different values and concepts. There is no relationship between them whatsoever. Control limits are calculated from process data for a particular control chart. An X-bar chart and an individual measurements chart will have different limits. They guide for process actions and tell you what the process is doing. Specification limits are chosen in numerous ways. They generally apply to the individual item being measured and appear on histograms, box plots, or probability plots. They separate good items from bad and tell you what we want the process to do. Again, control limits are not specification limits. Orange dashes are the control limits, while the red lines are the specification limits. Please follow the steps to make a control limits chart. 1. Determine the sample strategy and size. 2. Select the suitable control chart depending upon data type and sample size. 3. Collect data. 4. Calculate the statistics and the control limits. 5. Draw up control charts. 6. Interpret the control charts. Take samples for control charts. The correct sampling strategy is important. A sample strategy for control charts contains both its size as well as the frequency with which the sample is taken. This means always take a sample of a specific size at a set point in time or after a specific number of parts. In terms of timing, always select the samples so that they deliver the most meaningful statement on how the process is developing. Continuous data. 2 graphs are drawn up for control charts with continuous data material. In the first, the mean value, or the single values per group, are entered. In the second, the range, or standard deviation of each subgroup. Control limits of ±3 standard deviation are normally used. 99.73% of data thus lie within these limits, given normal distribution. Discrete data. 1 graph is drawn up for discrete data material in which one can enter, for example, the proportion or number of defective parts, the number of defectives, or the defects per unit of each subgroup. The table shows the different type of control charts and how to select the suitable control chart depending on the data type and sample size. For the first type of the attribute, data classification, which is number of defects per unit, we either use for the fixed opportunity, the C chart, or we use for the variable opportunity, the U chart, both based on B nominal distribution. For the second type of the attribute, data count, which is proportion defective parts, we either use for the fixed opportunity, the NP chart, or we use for the variable opportunity, the P chart, both based on Poisson distribution. For the measurement, continuous data, we use one of three types, depending on the subgroup size. For subgroup size of 1, we use IMR chart. For subgroup size less than 10, we use X bar and R chart. For subgroup size greater than 10, we use X bar and S chart. Continuous data control charts based on normal distribution. After collecting data, they will be written in a template, same as shown. The template is divided in 4 sections. First is the title, which briefly describes the information which is displayed. Second is the legend. This is information on how and when the data is collected. Third, data collection section. The counts or measurements are recorded in this section of control chart prior to be graphed in time sequence. Fourth, the average and the range calculation area. The calculated averages and range of the subgroups will be entered here. Here is the table, which is used to calculate the control chart's statistics and limits for continuous data manually. During the next 2 lectures, we will see how to determine these statistics and limits manually in details, and how to determine them using Sigma XL and Minitab. Here is the table for the constants, which are used to calculate the control chart's statistics and limits manually. Here is the table, which is used to calculate the control chart's statistics and limits for discrete data manually. During the next 2 lectures, we will see how to determine these statistics and limits manually in details, and using Sigma XL and Minitab. Thank you. See you in the second lecture of Control Phase module.